There is a patch of sky directly above the constellation Fornax in the southern hemisphere that looks to the naked eye like absolutely nothing. No bright star sits there, no cluster, no nebula, no visible smear of distant light, just black. The deep, ordinary black of a night sky between objects. That patch of sky is approximately as wide as a grain of sand held at arm's length against a dark field. That is not a poetic exaggeration. That is a precise measurement made by the astronomers who decided to point a $10 billion space telescope at it and hold it there for 10 hours. When the data came back, that grain of sand contained thousands of galaxies. Some of them were close, in cosmological terms, only a few billion light-years away, their light arriving fat and warm in the near-infrared, their spiral arms just barely resolved. Some were farther, their light more deeply reddened by expansion, their shapes compressed into faint elliptical smears, and some were at distances that the word distance does not adequately describe, because the universe was so much smaller when their light departed that the space between them and us has grown by more than a factor of 10 since then. In that grain of sand among those thousands of galaxies, one stood apart. It was not the largest in the image, it was not the brightest. From a purely visual standpoint, it was a faint smear, elongated slightly, one half bluish, one half reddened. The kind of object that in any earlier telescope era would have been catalogued as a smudge too faint to characterize and moved on from. But the James Webb Space Telescope is not any earlier telescope era. When the instrument called NIRSpec, the near-infrared spectrograph, stared at that faint smear for 10 uninterrupted hours and broke its light apart into its component wavelengths, what came back was something the team had hoped for but had not fully prepared to receive. A redshift of 14.32, a number that corresponds to a single, specific, irreversible moment in the history of the universe. The galaxy had emitted that light 290 million years after the Big Bang. The universe, at that moment, was 2% of the age it is now. Our own solar system would not exist for another 9 billion years. The atoms that currently compose the ground beneath wherever you are listening to this had not yet been forged. There were no rocky planets. There were, in all likelihood, very few second-generation stars anywhere in the observable universe. The epoch the models described at that distance was one of gradual awakening, slow cooling, the first dim structures assembling themselves from the raw hydrogen and helium left over from a universe that had only recently become transparent. And yet here was a galaxy, not dim, not fragile, not barely holding together, over 1,600 light-years across, several 100 million times the mass of our sun, bright with the light of young stars burning at full intensity, and carrying in the chemistry of its light the unmistakable signature of oxygen, an element that the Big Bang did not produce, an element that can only exist if stars have already been born, have already fused hydrogen and helium into heavier elements at their cores, have already died, and have already scattered those elements back into the gas around them, seeding the next generation. Stars had already completed their full life cycles inside this galaxy, at a moment when the universe was 290 million years old. The lead researcher, Stefano Carniani of the Scuola Normale Superiore in Pisa, Italy, described the result with a word that kept appearing in the papers and the announcements and the interviews that followed. Stunning. It is stunning, he said, that the universe can make such a galaxy in only 300 million years. Brant Robertson, professor of astronomy and astrophysics at the University of California, Santa Cruz, who co-led the survey team, said the discovery was completely unanticipated and likely to be seen as the most significant extragalactic discovery made with the James Webb Space Telescope to date. Tonight, we are going to sit with that discovery. We are not going to rush through it. We are going to follow it slowly, one layer at a time, from the telescope that found it to the galaxy it found to the oxygen it contained to what all of that means for our understanding of how the universe built itself in its earliest moments. This is the story of JADES-GS-Z14-0. A galaxy that should not exist. A galaxy that, in its scale and its chemistry, and the way it produces its light, looks more like a piece of our own Milky Way than anything the model said should be present in the universe at that age. Let the universe explain itself. We have time. To understand why this galaxy matters, you need to understand the instrument that found it. Not because the engineering is interesting in isolation, though it is extraordinarily interesting, but because the specific capabilities of the James Webb Space Telescope are not incidental to the discovery. They are the reason the discovery was possible at all. Before the James Webb Space Telescope, the oldest confirmed galaxy in the observable universe dated to approximately 320 million years after the Big Bang. It was called JADES-GS-Z 13-0, a galaxy in the same survey field, found by the same program, and it was already remarkable enough that its confirmation in late 2022 attracted significant attention. Before that, the record holder had dated to roughly 400 million years after the Big Bang. Before Hubble's deepest observations, we could not reliably see anything from the first billion years of cosmic history at all. Each of these milestones was not simply a matter of building a bigger mirror, it was a matter of physics. The universe expands. As it expands, the light travelling through it is stretched. A photon that left a galaxy in the first 300 million years of cosmic history, when the universe was compact and hot and the distance between that galaxy and where Earth would eventually be was measured in tens of millions of light years rather than billions, has been travelling ever since. And as it has travelled, the space it moves through has expanded, stretching the photon's wavelength the way you would stretch a wave drawn on a rubber band by pulling the ends apart. A photon that began its journey as visible light in the blue or green range of the spectrum will arrive at Earth after 13.5 billion years of travel shifted so far toward the red that it is no longer visible light at all. It is infrared radiation. It is heat, in the loose sense that all electromagnetic radiation carries energy. Its wavelength, when it arrives, is many times longer than when it departed. This process is called redshift. The number assigned to a galaxy's redshift describes how much the light has been stretched. A redshift of 1 means the wavelength has doubled. A redshift of 5 means the wavelength arriving at the detector is 6 times longer than when it left the source. A redshift of 14.32, the confirmed value for JADES-GS-Z 14-0, means the light arriving in the James Webb Space Telescope's instruments has been stretched to more than 15 times its original wavelength. Light that began its journey as ultraviolet radiation arrives, after 13.5 billion years of travel, as mid-infrared. Hubble could not see it. The Hubble Space Telescope, for all of its extraordinary capabilities, its ultraviolet and visible and near-infrared detectors, its ability to produce some of the deepest images of the universe ever captured, was simply not sensitive to the wavelengths in which the oldest light arrives. It was listening, very carefully and very precisely, on the wrong frequency. The James Webb Space Telescope was built to listen on the right one. Its primary mirror measures 6.5 meters across. 18 hexagonal segments, each coated in a microscopically thin layer of gold chosen specifically for its reflectivity in the infrared range, assembled in space after launch into a single continuous collecting surface. Hubble's primary mirror measures 2.4 meters. The Webb mirror collects roughly 5 times as much light per second, but the size comparison understates the difference, because light collecting area scales with the square of the diameter. More importantly, the Webb instruments are sensitive to infrared wavelengths, stretching from just below what the human eye can detect all the way out to wavelengths nearly 29 times longer than the reddest light we can see. This shift in sensitivity is not a technical detail, it is the entire story. But the mirror and the detectors are only part of the engineering challenge. Infrared detectors generate their own thermal noise. Any warm object emits infrared radiation. If the telescope's own components were warm, their heat would flood the instruments with noise and render the faint infrared glow of a galaxy from 290 million years after the Big Bang completely invisible. The telescope's instruments need to be cold. Specifically, they need to be held at approximately negative 233 degrees Celsius, just 40 degrees above absolute zero, cold enough that their thermal emissions fall below the level of the faintest signals they are designed to detect. To achieve that temperature in space, where the primary heat sources are the Sun, the Earth, and the Moon, the telescope carries a sunshield the size of a tennis court. 5 layers of reflective material that together reduce the heat reaching the instruments by a factor of roughly 1 million. That sunshield needed to fold tightly enough to fit inside the nose cone of the Ariane 5 rocket that carried the telescope into space, and then unfold flawlessly in the vacuum between the Earth and the point nearly 1 million miles away where the telescope was headed. On Christmas morning of 2021, the Ariane 5 rocket lifted off from the Guiana Space Center in French Guiana. Inside its nose cone was the most complex machine humanity had ever attempted to send beyond Earth's atmosphere. Engineers at the Space Telescope Science Institute in Baltimore had catalogued 344 single points of failure in the sequence of events that would follow. 344 individual steps, each of which, if it failed, would end the mission permanently. The telescope was destined for a gravitational balance point called Lagrange 2, nearly 1 million miles from Earth, at the precise location in space where the gravitational pulls of the Earth and the Sun cancel each other out, and an object can remain in a stable orbit relative to our planet, while also keeping a constant face toward the inner solar system. The advantage of Lagrange 2 is that the sun shield can remain permanently oriented between the telescope and the 3 heat sources it needs to block. The disadvantage is that Lagrange 2 is too far away for any repair mission. Hubble, positioned 340 miles above the Earth, was visited by astronauts 5 times during its operational life for maintenance and upgrades. The James Webb Space Telescope was sent somewhere no astronaut has ever been and none could reach. If anything went wrong after launch, it would remain there, drifting, operational for nothing, for as long as its orbit held. Nothing went wrong. All 344 steps executed correctly. The sunshield unfolded. The primary mirror segments aligned to a precision smaller than the wavelength of light. The instruments cooled to their operating temperatures. By mid-2022, science operations had begun. And within weeks, the data coming back was already exceeding the most optimistic projections of the people who built it. The first deep field image, released on July 11, 2022, targeted a galaxy cluster called SMACS 0723, approximately 5.12 billion light-years from Earth. The cluster itself was not the primary subject. A galaxy cluster at that distance contains so much concentrated mass that its gravity bends the light from objects behind it, producing a phenomenon called gravitational lensing. The Webb telescope was using the cluster as a natural magnifying glass, amplifying the faint light of objects further away that would otherwise be too dim to detect directly. What the image showed was thousands of galaxies, some close, some far, some smeared into arcs by the gravitational field of the foreground cluster. Many of them had never been seen before. The patch of sky covered was, again, approximately the size of a grain of sand held at arm's length. Researchers posted comparisons to Hubble's observations of the same field within hours. Galaxies that Hubble had spent 11 days capturing as faint, characterless smudges at the very limit of its detection appeared in the Webb image with visible structure, with colour gradients, with features that the older telescope had been physically incapable of resolving. One astronomer described the experience as being equivalent to putting on glasses for the first time, except the glasses were showing things that had been theoretically expected to exist, but had never been directly observed. The JADES program, the JWST Advanced Deep Extragalactic Survey, had been in development before the telescope launched. It was the most ambitious systematic attempt to study the earliest galaxies ever designed, led by Daniel Eisenstein at the Harvard and Smithsonian Center for Astrophysics, with co-investigators including Kevin Hainline at the University of Arizona, Brant Robertson at the University of California, Santa Cruz, and Ben Johnson, also at the Center for Astrophysics. The survey targeted 2 fields in the southern sky, the Goods North and Goods South fields, the same regions where Hubble had accumulated some of its deepest observations over years of careful pointing. The overlap was deliberate. Every galaxy Hubble had detected there would serve as a baseline and a calibration point. Everything beyond Hubble's reach would be new. The difference in capability, considered from one direction to another, is the difference between seeing that a sound exists somewhere in a distant building and being able to identify every individual voice in every room, not an improvement, a transformation. A NIRSPEC, the near-infrared spectrograph aboard the James Webb Space Telescope, can take precise spectra of hundreds of objects simultaneously, measuring the exact wavelengths of emission and absorption lines in dozens of galaxies at once, and deriving from those measurements their precise distances, their chemical compositions, their temperatures, the masses of their stars, and the dynamics of their gas. This is not something Hubble could do for objects at those distances, Hubble could photograph them, faintly. Webb could read them. In October of 2023, the JADES team conducted 5 full days of continuous imaging with NIRCam on a single field, producing what they called the JADES Origins field. The depth of that imaging, combined with specialized filters designed to isolate the light signatures of the earliest galaxies, identified candidates at distances that required spectroscopic confirmation before any claims could be made. In January of 2024, the NIRSpec instrument observed those candidates for spectroscopic confirmation. One of them, designated JADES GS Z14-0 in the survey catalogue, received 10 hours of continuous spectroscopic observation. When the spectrum was processed, the result was unambiguous, a redshift of 14.32, the most distant galaxy ever confirmed by direct spectroscopic measurement at that time. Its light had left it when the universe was 290 million years old. It had been travelling toward us ever since. The team had found what they were looking for. They had not been prepared for what it would look like when they found it. The models that existed before the James Webb Space Telescope were built from decades of careful observation and theoretical work. They described a universe that had a specific, well-understood developmental sequence. After the Big Bang, the universe was hot, dense, and opaque. Photons could not travel freely because they were constantly scattering off the fog of charged particles that filled all of space. For roughly 380,000 years, the universe remained in this opaque, superheated state. Then, as the universe expanded and cooled enough for electrons and protons to combine into neutral hydrogen atoms, the fog cleared. The photons that had been trapped released all at once, streaming freely through space in every direction. The afterglow of that moment is still detectable today as the cosmic microwave background radiation, the faint, cold echo of that first transparency, arriving at Earth from every direction in the sky, at a temperature just 2.7 degrees above absolute zero. After recombination, as the clearing of the fog is called, the universe entered a period known as the Cosmic Dark Ages. There were no stars, there were no galaxies, there were no sources of visible light of any kind, just hydrogen and helium gas, very slightly lumpy from the quantum fluctuations of the Big Bang, cooling and drifting in an expanding darkness that lasted for tens of millions, and perhaps hundreds of millions of years. Then gravity did what gravity does. The slightly denser regions of gas pulled in the surrounding material. The slightly less dense regions emptied. Slowly at first, then faster. Dark matter, the invisible gravitational scaffolding that comprises the majority of matter in the universe, began collapsing into halos, regions of concentrated gravitational potential. Ordinary matter, hydrogen and helium gas, fell into those dark matter halos, compressed under its own weight, heated, cooled, fragmented, and eventually collapsed further still into the first stars. This process, the model said, took time, a great deal of time. The first stars were expected to ignite somewhere around 100 to 400 million years after the Big Bang, depending on which simulation you trusted. They would be small by the standards of the first galactic populations, embedded in dark matter halos that were themselves small, because the hierarchical assembly of structure meant that small things came first, and larger things were built from smaller pieces through mergers and accretion over long periods. A galaxy comparable in any way to the ones that exist in the present-day universe, with substantial stellar mass, complex chemistry and organized structure, was not expected at anything near those early epochs. The models gave the universe hundreds of millions of years to build its first modest structures, and then billions more to assemble those into anything we would recognize as a mature galaxy. JADES-GS-Z14-0 was not supposed to be there at 290 million years, and yet it was. And its properties, each one individually surprising and collectively astonishing, were not ambiguous. They were precisely measured by an instrument that could not be wrong about what it was seeing. The galaxy's diameter, measured from the images, is over 1,600 light-years. That number requires a comparison to be meaningful. The Milky Way, our own galaxy, is approximately 100,000 light-years in diameter. In that sense, 1,600 light-years sounds small, and it is small by galactic standards. But the Milky Way took billions of years to grow to that size. At 290 million years after the Big Bang, no galaxy in the standard model was expected to have grown to anything close to 1,600 light-years in diameter, because the hierarchical assembly of structure simply had not had enough time to operate at that scale. More importantly, the 1,600 light-year measurement situates J0 Z14 precisely in terms that make the looks like ours comparison meaningful. The Orion arm of the Milky Way, the spiral arm in which our own solar system resides, is approximately 1,600 light-years wide. The arm where we live, the region of our own galaxy that contains our sun and our planet, and every place any human being has ever been, is the same width as this entire ancient galaxy. The reason that comparison matters is not primarily about size. It is about what the size tells us about how the galaxy produces its light. Many distant luminous galaxies in the early universe produce most of their light not from stars, but from the accretion disk of a central supermassive black hole. When matter falls into a black hole, the friction and compression in the infalling gas heats it to extraordinary temperatures, producing enormous amounts of radiation across a wide range of wavelengths. A galaxy whose luminosity is driven by a central black hole called a quasar appears very bright but is physically very compact, because the light comes from a region very close to the black hole itself. JADES-GS-Z14-0 is 600 light-years across. That is too large to be a quasar. The light cannot be coming from a compact central engine. For a galaxy to be that large and that bright, the light must be distributed across its entire extent. It must be coming from stars. Many stars. Young, hot, intensely radiating stars burning hydrogen at the full rate. The team confirmed this through the spectral energy distribution of the galaxy's light, the way its brightness varies across different wavelengths. The pattern matched star formation, not black hole accretion. The galaxy's mass in stars derived from that analysis was estimated at several 100 million times the mass of our Sun. Several 100 million solar masses of stars in a galaxy that assembled itself within 290 million years of the Big Bang. The standard model of galaxy formation had a specific prediction for what the first substantial galaxies should look like at that epoch. They should be small, with stellar masses typically in the range of a few million to tens of millions of solar masses, representing the very first stages of hierarchical assembly. A galaxy with several 100 million solar masses at redshift 14 was not just unexpected. It was, in the language of the researchers who found it, completely unanticipated. Brant Robertson put the significance plainly in the announcement that followed the spectroscopic confirmation. He said the discovery was not just a new distance record. The most important aspect of JADES-GS-Z14-0, he said, was what it was. Its brightness, its size, its stellar origin. The fact that it could have been detected even if it were 10 times fainter, which implied that galaxies like it, or larger, might exist at even earlier times, perhaps in the first 200 million years after the Big Bang, still waiting to be found. And that was before anyone checked the chemistry. The spectroscopic data from RANIER-SPEC provided more than the redshift. It provided a window into the galaxy's composition. The brightness of the source at certain wavelengths, particularly as measured by MIRI, the mid-infrared instrument aboard the telescope, indicated the presence of strong ionized gas emission, the signature of energetically active regions where young stars are heating the surrounding gas and causing it to glow. Among those ionized gas signatures was one that drew immediate attention: oxygen, not trace amounts, not a marginal detection at the limits of the instrument's sensitivity. Bright emission lines from hydrogen and oxygen, confirming that this galaxy, 290 million years after the Big Bang, contained both of the two most abundant elements that stars produce and distribute when they live and die. Jake Helton of Steward Observatory and the University of Arizona, who led the analysis of the MIRI observations, noted that the brightness of the source at longer wavelengths was higher than would be predicted by simply extrapolating from the shorter wavelength measurements. That excess brightness indicated the presence of those strong emission lines, and those emission lines indicated chemistry that the universe at that age was not supposed to have. The team stated in their announcement with the precise measured language that scientific announcements require, the presence of oxygen so early in the life of this galaxy is a surprise and suggests that multiple generations of very massive stars had already lived their lives before we observed the galaxy. Multiple generations, at 290 million years after the Big Bang. When Stefano described the result as stunning, he was not using the word for rhetorical emphasis. He He was using it because the only honest response to data that contradicts your most carefully constructed models with that degree of precision and that degree of repeatability is the experience of being stopped in place by something you did not expect. The galaxy they had found was, in its scale and its luminosity and the nature of its light, something that would not have seemed out of place in the universe of several billion years ago. It was not what the earliest universe was supposed to have, and it was definitely not what anyone had expected to find in a 10-hour exposure of a patch of sky the size of a grain of sand held at arm's length. Let that settle for a moment. The universe, at 290 million years old, had already built something that takes billions of years to build. It had done it so efficiently that the people whose careers were built on the models that describe how it should have worked described the discovery, in the official language of peer-reviewed science, as completely unanticipated. The question is not merely what JADES-GS-Z14-0 is, the question is what it means that it exists at all. And to begin answering that question, you need to understand the one element in its spectrum that carries the most information about the timeline of the universe's early history. You need to understand what it means that there is oxygen in a galaxy that old. There is a hierarchy to the elements, and understanding it is essential to understanding why oxygen in JADES-GS-Z14-0 is not just chemically interesting, but cosmologically transformative. The Big Bang produced three elements in meaningful quantities: hydrogen, the simplest atom, a single proton, and a single electron, comprising roughly 75% of all the ordinary matter in the universe. Helium, 2 protons and 2 electrons, comprising roughly 25%. And trace amounts of lithium, the third element, produced in quantities so small that you could spend a lifetime cataloguing galaxies and never find a star with a noticeable lithium signature relative to the dominant hydrogen and helium around it. Everything else on the periodic table, every element heavier than lithium, was made after the Big Bang. Not in the Big Bang itself, but in the interiors of stars, in the nuclear forges at the cores of stars that burn hot enough and dense enough to fuse lighter nuclei into heavier ones, step by step releasing energy as they go. Carbon, nitrogen, oxygen, neon, magnesium, silicon, all the way up to iron, the point at which fusion stops releasing energy and starts consuming it. Oxygen is the third most abundant element in the universe by mass. It is also, crucially, not primordial. It was not present in the gas from which the first stars formed. Every atom of oxygen in the universe was produced inside a star, and then released into space only when that star died. The mechanism of release matters. Stars below a certain mass, stars like our own Sun, shed their outer layers at the end of their lives in a process that gradually expands the star into a red giant, and then blows off its outer envelope as a planetary nebula, leaving behind a dense, cooling remnant called a white dwarf. In this process, the elements synthesized at the star's core can be distributed into the surrounding interstellar medium, eventually to be incorporated into the next generation of gas clouds and stars. Stars above a certain mass, roughly 8 times the mass of our Sun or more, end their lives more violently. When they exhaust their nuclear fuel and can no longer support themselves against gravity, their cores collapse in a fraction of a second, releasing an enormous amount of energy in the form of neutrinos and a shock wave that tears apart the outer layers of the star and disperses them at thousands of kilometers per second into the surrounding space. This is a supernova, the most energetic sustained event in the observable universe outside of the Big Bang itself. Supernovae are extraordinarily efficient at distributing heavy elements. A single supernova can scatter the oxygen, carbon, nitrogen, and heavier elements, produced over a massive star's lifetime, across hundreds of light years, in a matter of tens of thousands of years, enriching the surrounding gas with the chemical products of that star's entire nuclear history. The most massive stars, those with dozens of times the mass of our Sun, live for only a few million years before this violent ending, which means that from the perspective of the universe's timeline, even the most massive stars complete their full life cycle relatively quickly. A few million years. In a universe that is currently 13.8 billion years old. But in a universe that is 290 million years old, a few million years is not negligible. It is a meaningful fraction of the total time that has passed since the Big Bang. And for oxygen to be present in JADES-GS-Z14-0 at 290 million years the following chain of events needed to have been completed within that window. First, the first generation of stars needed to form. The raw hydrogen and helium gas of the early universe needed to collapse into dark matter halos, cool, fragment, and ignite as stars. Under the models that existed before Webb, this was expected to begin happening somewhere between 100 and 200 million years after the Big Bang, with the caveat that the very first stellar populations might form as early as 100 million years or as late as several hundred million, depending on the details of how dark matter halos assembled and how efficiently gas cooled within them. Then, those first stars needed to live out their full lifespans. The most massive stars in the first generation, the population 3 stars as they are called in the nomenclature of stellar astronomy, the stars that formed from nearly pure hydrogen and helium and contained essentially no metals in the astronomical sense, which refers to all elements heavier than helium. Those stars are theorized to have been extremely massive, in some models hundreds of times the mass of our Sun, because the absence of heavy elements that allow gas to cool efficiently meant that the first star-forming clouds had to compress to much higher temperatures and pressures before fragmentation, producing stars of enormous size. Massive stars burn hot and fast. The most massive among the first generation would have lived for only a few million years before going supernova. Then, those supernovae needed to enrich the surrounding gas with the oxygen and other heavy elements they produced, and that enriched gas needed to cool and collapse and form a second generation of stars in a galaxy that had already grown large enough to contain several 100 million solar masses worth of stars. All of this, beginning to end, in 290 million years or less. In March of 2025, a team of researchers, including Stefano Carniani, who had led the original Discovery team, and collaborators using the Atacama Large Millimeter Array, the network of 66 radio telescope dishes in Chile's Atacama Desert, operating at millimeter and sub-millimeter wavelengths, announced the spectroscopic conformation of oxygen in JADES GS Z14-0. Their measurement gave the galaxy's redshift at 14.1793 plus or minus 0.0007, consistent with and slightly refined from the earlier NIR spec measurement, and confirmed the detection of the O3 emission line, the spectroscopic signature of doubly ionized oxygen, at that distance. The Atacama Large Millimeter Array can detect this line because it has been redshifted from its rest frame wavelength in the far ultraviolet down to millimeter wavelengths where the array's dishes are sensitive. The detection was unambiguous, the oxygen was there. The announcement stated clearly that this marked the most distant observation of oxygen to date. The presence of oxygen at that epoch, the researchers noted, suggests that the galaxy underwent rapid formation and chemical maturation, challenging previous assumptions about the timeline of heavy element production in the early universe. Challenging previous assumptions is a phrase that carries a great deal of weight in scientific literature. It is not used lightly. When a paper published in a peer-reviewed journal says that a result challenges previous assumptions, what it means in practice is that the result is sufficiently well established and sufficiently inconsistent with the existing framework that the existing framework needs to be revised, not thrown out, not abandoned, but revised, updated, extended to accommodate something it did not previously account for. What the oxygen in JADES-GS-Z14-0 challenged was the assumption that the early universe operated on a certain developmental timescale, the assumption that structure formation, star formation, chemical enrichment, and the assembly of galaxies proceeded at rates that were determined by the densities and temperatures and expansion rate of the early universe in ways that the standard models had carefully calibrated. Those models had been calibrated without knowledge of a galaxy like this. Think about the compression of time involved. The first generation of stars forming from pure hydrogen and helium. Those stars living their full lifespans. The most massive of them going supernova and distributing oxygen into the surrounding gas. That enriched gas cooling and collapsing into a second generation of stars. That second generation assembling, along with dark matter and more accreting gas, into a galaxy that is over 1,600 light-years across and contains hundreds of millions of solar masses of stars. All of that happened, according to the data, before the universe was 300 million years old. The timeline required is tight, uncomfortably tight, by the standards of the models. Not impossible, because the physics that governs star formation and supernova enrichment does not prohibit it in principle. But the efficiency required, the fraction of available gas that needed to be converted into stars, the rate at which those stars needed to form and evolve, the speed at which the enriched material needed to cool and collapse into the next generation, all of these parameters need to be at or near the maximum values the physics allows. In the present-day universe, galaxies typically convert between 5 and 10% of their available gas into stars over their lifetimes. This low efficiency is partly a consequence of the feedback processes by which young stars heat and stir and sometimes expel the gas around them, making it harder for more of the gas to collapse and form stars in turn. For JADES-GS-Z14-0 to have assembled the stellar mass, it appears to have assembled within 290 million years. The efficiency would need to have been dramatically higher. Some researchers have suggested that the early universe, which was denser and hotter and had not yet been stirred by billions of years of stellar feedback, may have allowed for star formation efficiencies that are simply not achievable in the present epoch. The gas was denser. The conditions for collapse were more favourable. The feedback from early stars may have been less effective at disrupting the surrounding material. This is a possible explanation. It is not a confirmed one. What is confirmed is the observation. And the observation is that at 290 million years after the Big Bang, a galaxy existed that had already cycled through enough stellar generations to produce detectable oxygen, had assembled enough stellar mass to be one of the brightest objects at that epoch, and was extended enough in space to rule out a central black hole as the source of its luminosity. Stefano Carniani, in a statement around the time of the oxygen detection confirmation, described the finding as completely unanticipated. That word again. The same word Brant Robertson had used when the galaxy was first confirmed. The same word that kept appearing in the papers and the presentations and the formal announcements from the various teams who looked at the data and tried to fit it into the framework they had spent their careers building. Completely unanticipated. There is something clarifying about that phrase, heard repeatedly from the mouths of the most accomplished observational cosmologists in the world. It does not signal a crisis, in the sense of a fundamental collapse of understanding. It signals something more precise and, in its way, more exciting. It signals a discovery that is so cleanly outside the bounds of what existing knowledge predicted that the existing knowledge must be extended to include it. The universe, it turns out, was working faster than anyone had calculated, and JADES-GS-Z14-0 is not the only evidence for that. JADES-GS-Z14-0 did not emerge from a vacuum. Its discovery was the sharpest and most specific single data point in a much larger pattern that had been building since the James Webb Space Telescope's first deep-field images arrived in the summer of 2022. In those first images, before the JADES survey had produced its deepest results, before the spectroscopic confirmation programs had refined the distances to the earliest candidates, astronomers began noticing something that required careful consideration. There were a great many galaxies in the early universe that appeared, based on their brightness and estimated distances, to be more massive than they should be. The standard model of cosmic structure formation, the lambda CDM model, which stands for lambda cold dark matter and describes a universe dominated by a cosmological constant and cold dark matter as the primary structural ingredient, makes specific predictions about the number and mass distribution of galaxies at different epochs. It says how many galaxies of a given mass should exist at a given redshift, based on simulations of how dark matter halos form and merge and accumulate gas over time. What the first year of Webb observation showed, across multiple independent survey programs targeting different regions of the sky, was that the number of bright, apparently massive galaxies in the early universe was larger than those predictions allowed for, substantially larger. Some estimates put the excess at a factor of 10 or more relative to the model's predictions, at redshift above 10. These objects, the ones that seemed most egregiously to violate the model's expectations, were dubbed universe breakers in popular coverage of the findings. The name came from a Nature paper published in early 2023 by Ivo Labbe at Swinburne University in Melbourne, and colleagues who had analysed data from the Cosmic Evolution Early Release Science Survey and identified 6 galaxies formed within the first 500 to 700 million years after the Big Bang that appeared to contain stellar masses comparable to the Milky Way. each estimated to contain between 10 billion and 100 billion times the mass of a typical star. For context, the Milky Way is a moderately large galaxy. It contains roughly 60 billion solar masses in stars. These 6 objects, forming when the universe was less than 5% of its current age, appeared to be comparable in stellar mass to some of the largest galaxies in the present-day universe. Under the Standard Model, that should have been physically impossible. The dark matter halos necessary to host such massive galaxies simply could not have grown large enough in the time available. Michael Boylan-Kolchin at the University of Texas at Austin, who had spent years developing theoretical predictions for early galaxy populations, wrote a companion paper in Nature Astronomy that described the observations as placing the Standard Model under severe tension. Erica Nelson, at the University of Colorado Boulder, who was part of the team that first identified the anomalous objects, described them as absolutely wild, adding that they implied either an early universe more chaotic and efficient than any model had assumed, or a universe in which the physical processes governing star formation operated under rules that had not yet been identified. The scientific response was careful, multi-layered, and ultimately more nuanced than the initial coverage suggested. One of the most important revisions came from work led by Katherine Chorowski, a graduate student at the University of Texas at Austin, working with Stephen Finkelstein, whose team reanalyzed a large sample of early galaxies observed by Webb and found that a significant fraction of the apparently massive objects were not, in fact, as massive as they appeared. The issue was the light itself. When a galaxy contains a rapidly accreting supermassive black hole at its center, the region around that black hole, the accretion disk and the broadline region, emits enormous amounts of light across a wide range of wavelengths. That light, if not properly accounted for, inflates the estimate of a galaxy's stellar mass, because the standard methods for estimating mass from brightness assume that all the light is coming from stars. If a significant fraction is coming from a central black hole, the mass estimate will be systematically too high. A class of objects called little red dots, named for their compact appearance and their distinctively red colour, appeared to account for many of the most extreme, apparently massive early galaxies. These objects are now thought to be dominated by light from central black holes rather than stars, and when they were removed from the analysis, the remaining early galaxies were, in Finkelstein's words, not too massive to fit within predictions of the Standard Model. Finkelstein stated directly that the bottom line was that there is no crisis in terms of the Standard Model of cosmology, a theory that has stood the test of time as long as this one requires overwhelming evidence to really throw it out, and the data, once the little red dots were properly accounted for, did not rise to that standard. But the full picture is more qualified than that summary makes it sound. Even after removing the little red dots and properly accounting for the contribution of black hole light to galaxy luminosities, there remained a residual excess. There are still roughly twice as many massive galaxies in Webb's early universe data as the Standard Model predicts. Chorowski noted this directly. There are more galaxies than predicted, even if none of them are so massive that they break the universe. The explanation most frequently advanced for this residual excess is that star formation in the early universe was more efficient than it is today. Perhaps because the gas was denser, perhaps because the feedback processes that disrupt star formation in the present epoch, the energetic radiation and stellar winds and supernova shockwaves that heat and expel surrounding gas and slow down the collapse of new star-forming regions, operated with less effectiveness in the early universe, where conditions were different and the physics of star-forming clouds was not yet governed by the cumulative effects of billions of years of stellar evolution. This is a reasonable hypothesis. It is consistent with the data. It does not require abandoning the Standard Model. It requires refining it, extending it to include star formation efficiencies at early times that are higher than the values calibrated from the present-day universe. What it does not do is make JADES-GS-Z14-0 less remarkable. JADES-GS-Z14-0 is not one of the little red dots. It is not a galaxy whose apparent mass is inflated by a central black hole. Its size, over 1,600 light-years across, rules that out. Its light is definitively stellar in origin. Its stellar mass is real. Its oxygen is confirmed by independent observations from a ground-based radio telescope array in Chile. Its redshift is spectroscopically confirmed at 14.32. It is the archetype, as Stefano Carniani described it, of a phenomenon that was not supposed to exist. the clearest, sharpest, most well-characterized single example of the general pattern that Webb has been revealing since its first deep exposures. The early universe was more productive, more efficient, more chemically advanced than the standard models predicted it should be. The standard model is not broken, but it is being revised, and the revision it requires at the earliest epochs, where the data is most surprising and the discrepancy between observation and prediction is most persistent, is still an active area of research. Teams around the world are working with the Webb data to understand whether the residual excess of early massive galaxies reflects a gap in our understanding of star formation efficiencies, or a gap in our understanding of dark matter, or a gap in our understanding of the initial conditions of the universe set during the period of rapid expansion called inflation that occurred in the first fractions of a second after the Big Bang. None of these explanations has achieved consensus. All of them are being actively tested, and the James Webb Space Telescope is still accumulating data, still pointing at deep fields, still finding things that no model fully anticipated. In that context, it is worth pausing on what has been confirmed. A galaxy existed 290 million years after the Big Bang. It was large, bright, stellar, and chemically mature. It looked, in its scale and its mode of light production, more like a piece of our own galaxy than anything the model said should be present at that epoch. And in the oxygen detected in its spectrum by the most sensitive space telescope and the largest radio telescope array humanity has built, it told the story of stars that lived and died before our models expected the first ones to be born. That story is worth following through to wherever it leads. There is a moment in the history of the universe that astronomers call the cosmic dawn. It does not have a precise timestamp. It is not a single event, but a transition, the long, complicated process by which the first stars and galaxies ended the cosmic dark ages and transformed the universe from an opaque fog of neutral hydrogen into the transparent, structured, light-filled cosmos that has existed since. The cosmic dark ages lasted, by the best estimates based on the available evidence, from approximately 380,000 years after the Big Bang, when the cosmic microwave background photons were released as the universe became transparent for the first time, until somewhere between 100 million and 500 million years after the Big Bang, when the first luminous sources turned on and began the long process of rionizing the neutral hydrogen that filled the universe. That rionization, the epoch when the first ultraviolet radiation from the first stars and galaxies ionized the neutral hydrogen fog that had settled after recombination, is one of the most important transitions in cosmic history. It changed the universe from opaque, at least to certain wavelengths, to transparent again, but this time permanently. It marked the moment when the universe became the place we can observe, where photons travel freely from their sources to our telescopes across billions of light-years of intervening space. Before the cosmic dawn, nothing we can observe directly existed. Everything that came before was dark. JADES-GS-Z-14-0 exist inside the cosmic dawn. It is not from before the first stars, but it is contemporary with the earliest stellar populations that are theorized to have existed. It formed and grew and produced oxygen while the universe was still in the process of becoming luminous, while the neutral hydrogen fog was still being burned away by the radiation from the first galaxies, while the universe was barely past the threshold of its first light. The program that found it, the JADES survey, was specifically designed to study this transition. The name reflects the scientific objective. The JWST Advanced Deep Extragalactic Survey was built to map the earliest galaxies, to understand how they formed and grew and contributed to the reionization of the universe, and to test whether the predictions of the standard model held up at the most extreme distances accessible to the telescope. The people who designed the survey had specific predictions in mind. They expected to find galaxies at these distances that were consistent with what the simulations described: small, faint, relatively low in stellar mass, dominated by the first generation of stars, chemically pristine or nearly so, without the heavy elements that come from multiple cycles of stellar birth and death. What they found in JADES-GS-Z-14-0 and in the broader population of early galaxies that the survey revealed was something systematically different from those predictions. Not different in kind, not different in the sense that galaxies did not exist, or that the universe did not form structure. Different in degree, different in scale, different in the efficiency with which the early universe converted gas into stars and assembled those stars into organised, chemically evolved systems. The JADES team published their first major spectroscopic results in January of 2023 in Nature Astronomy. The team, led by Emma Curtis Lake at the University of Hertfordshire, provided spectroscopic confirmation of 4 galaxies at redshifts between 10.3 and 13.2, corresponding to a period when the universe was between 300 and 450 million years old. These were direct measurements based on the specific wavelengths of known emission lines shifted by known amounts, confirming beyond any methodological ambiguity where in the universe's history these objects existed. At the time of publication, they were the most distant spectroscopically confirmed galaxies ever recorded. The galaxies appeared to contain more stars than models of galaxy formation at those epochs predicted should be there. They were not faint smudges at the edge of the theoretically expected distribution. They were in several cases bright and structured, suggesting substantial stellar populations that had been building for longer than the models allowed. A galaxy at redshift 13 requires that its stars began forming within the first few hundred million years after the Big Bang. Under the standard model, that process should have been slow and modest. The data was saying something different, and the direction of the discrepancy, from the very first confirmed detections, was consistent. More mass, more brightness, more chemical complexity, more organisational maturity, at earlier times than the models predicted. This consistency across independent survey programs, across different instruments and different fields of the sky, and different analysis methodologies, is what transforms a collection of surprising individual observations into a systematic finding. The Cosmic Evolution, Early Release Science Survey, the CEERS survey, led by Stephen Finkelstein at the University of Texas at Austin, catalogued hundreds of candidate galaxies from the first 650 million years of cosmic history. The Cosmos Webb survey, co-led by Caitlin Casey at the University of California, Santa Barbara, mapped a larger area of sky than any previous Webb survey and ultimately catalogued roughly 800,000 galaxies spanning the full range of cosmic history. Across these different programs, the same pattern persisted. The early universe contained more luminous galaxies than the models predicted. The degree of excess was debated, refined, partially explained by the identification of the little red dots as black hole-dominated objects rather than star-dominated ones. But even after those corrections, the excess remained, even after the most conservative interpretations and the most careful accounting for every possible systematic error and observational bias. The early universe was producing bright, massive, chemically active galaxies at a rate that the models had not anticipated. JADES-GS-Z 14-0 sits at the extreme end of this pattern. It is not just more massive and more luminous than expected. It is more massive and more luminous than expected at the most extreme distance, yet confirmed by any spectroscopic observation. It is not a statistical fluctuation in a population that is slightly larger than predicted. It is a single, precisely characterized object whose properties are individually astonishing and collectively require some revision to our understanding of how efficiently the universe operated in its earliest moments. The questions that follow from this finding do not have easy answers. They are the kinds of questions that require new theoretical frameworks, new simulations that can incorporate the higher efficiencies implied by the observations, new data that can test whether the pattern holds at even earlier times, and new observations that can characterize the properties of the galaxy population at the cosmic dawn with the precision that spectroscopy provides. The James Webb Space Telescope is still running. The surveys are still accumulating data. The archive of observations grows every week. And somewhere in that archive, or in the observations being planned right now by teams who have seen what JADES-GS-Z 14-0 revealed and want to push further, there may be a galaxy from an even earlier epoch, one that carries the same message about the early universe's efficiency, the same chemical fingerprints of stars that lived and died before anyone expected them to exist, waiting in light that has been travelling toward us for even longer than the light of JADES-GS-Z 14-0. Grant Robertson said the team could have detected JADES-GS-Z 14-0, even if it were 10 times fainter. That means the detection threshold reaches into the first 200 million years. If the patterns that Webb has been finding at later times hold at even earlier ones, if the universe was running at the same elevated efficiency during its first 200 million years as it appears to have been running during its first 300 million, then the discoveries still ahead may be even more striking than the one that stopped a room full of experienced cosmologists in their tracks in January of 2024. That morning, when the NIRSpec spectrum of JDES GS Z140 was first processed and the redshift read out as 14.32, the researchers who saw it described the experience as incredibly exciting. A team that had spent years designing the survey, years commissioning the telescope, years waiting for data that might or might not produce something like this, seeing for the first time the spectrum of the most distant galaxy ever confirmed by direct measurement. The excitement was real. And it was not just about the record. It was about what the record meant for everything they thought they understood, about how the universe began building itself. There is a question that comes up whenever someone encounters the distance to JADES-GS-Z14-0 for the first time, and it is a genuinely interesting question about the nature of the universe. The light from JADES-GS-Z14-0 has been travelling toward Earth for 13.5 billion years, but the universe is only 13.8 billion years old. How can the galaxy be 33.8 billion light years away from us if the universe is only 13.8 billion years old and light travels at a fixed speed? The answer reveals something fundamental about the difference between the universe that physics describes and the intuitions that everyday experience provides. Light does travel at a fixed speed through space, roughly 300,000 kilometers per second in a vacuum. This is one of the most precisely measured and most robustly confirmed constants in all of physics. Nothing with mass can reach it. Information cannot travel faster than it, but the universe is not static. Space itself expands, and when space expands, the distances between objects that are not gravitationally bound to each other increase, not because those objects are moving through space, but because the space between them is growing. When JADES-GS-Z14-0 emitted the light that the James Webb Space Telescope eventually captured, that galaxy was much closer to us than 33.8 billion light years. The universe was 290 million years old. It had been expanding for 290 million years from a state of extremely high density and temperature. The distance between where JADES-GS-Z14-0 was and where our own galaxy would eventually be was, at that moment, relatively small by the standards of the present-day universe. As the light travelled toward us, the space through which it was travelling continued to expand. The galaxy moved away, not because it was moving through space in the conventional sense, but because the space between it and us was growing. By the time the light arrived at the James Webb Space Telescope, the universe had expanded so dramatically that the galaxy's current location, accounting for that entire history of expansion, is approximately 33.8 billion light-years away. This is what cosmologists mean by the co-moving distance to an object, as opposed to the light travel distance. The light travel distance to JADES-GS-Z14-0 is 13.5 billion light-years, because that is how long the light has been in transit. The co-moving distance, which represents where the galaxy is now in the expanded universe, accounting for all the expansion that has occurred since the light departed, is approximately 33.8 billion light-years. The fact that this is possible, that the co-moving distance can be larger than the age of the universe times the speed of light, is a direct consequence of the fact that the expansion of space is not governed by the same speed limit that applies to objects moving through space. Space itself can expand at any rate. There is no physical law that prohibits the universe from expanding at rates that would carry distant galaxies to co-moving distances greater than the product of their light travel time and the speed of light. Jake Helton of Steward Observatory and the University of Arizona, who was part of the JADES team, explained this precisely when asked about how any telescope could see a galaxy that is currently 33.8 billion light-years away in a universe that is only 13.8 billion years old. A cosmological horizon, he explained, is a maximum distance from which one could possibly retrieve information. The relevant horizon for detecting JADES-GS-Z14-0 is the maximum distance from which light could have travelled to us in the age of the universe, accounting for the expansion history, and JADES-GS-Z 14-0 was within that horizon when it emitted the light we are observing. In other words, there was once a causal connection between JAD ES-GS-Z 14-0 and us. That galaxy's light could reach us because, at the moment it was emitted, the space between us was small enough, and the light had enough time during its 13.5 billion year journey to close the gap. That connection is now severed. The galaxy is now so distant, and the expansion of space between it and us is now so fast that any signal sent from that galaxy today would never reach the Milky Way. The space between us is expanding faster than the light can cross it. That galaxy exists somewhere in the universe right now, 33.8 billion light-years away by co-moving distance. It has spent 13.5 billion years evolving since the moment we observed it. The stars that filled it at 290 million years after the Big Bang have long since lived their full lifespans. The galaxy itself has almost certainly grown, merged with neighbours, been incorporated into larger structures, or undergone whatever evolutionary history the universe had in store for it over 13.5 billion years. But we cannot see any of that. We can only see the galaxy as it was when the universe was 290 million years old. A snapshot frozen in the moment the light departed, preserved in transit for 13.5 billion years, and finally decoded by an instrument hovering 1 million miles from Earth in a gravitational balance point chosen specifically because its temperature environment allows the detectors to be cold enough to hear the faintest whisper of infrared radiation arriving from the earliest light of the cosmos. There is something genuinely profound about this. Every galaxy at a large redshift is not just far away. It is a message from a specific moment in the past. And the farther away it is, the earlier the moment the message describes. The James Webb Space Telescope, in collecting the light of JADES-GS-Z 14-0, was not just looking at a distant object. It was reading a letter that was written 13.5 billion years ago, before our solar system existed, before the Earth existed, before any of the atoms that compose any living thing on this planet had been assembled from stellar interiors and supernova remnants, and the long, slow chemistry of gas clouds and protoplanetary disks. That letter described a galaxy with oxygen in it. The oxygen atoms in JADES-GS-Z 14-0, or rather the atoms that produced the emission lines that revealed their presence, had been forged in stellar cores and distributed by supernovae in the first few 100 million years of the universe. The oxygen atoms in your body, the ones that compose your blood and your bones and every cell membrane in every cell of every tissue in your physical form, were forged in stellar cores too, in stars that lived and died in the Milky Way over the past several billion years. The process is the same, the timeline is different, but the physics is identical. Stars make oxygen, supernovae distribute it, gas clouds incorporate it. New generations of stars form from that enriched gas. Planets form around those stars, chemistry happens, and eventually on at least one of those planets, that chemistry becomes complex enough to build a space telescope, point it at the faintest patch of sky, and read the signature of oxygen in a galaxy from which no further signal will ever arrive. The universe has been doing this for 13.8 billion years. JADES-GS-Z 14-0 is a record of how it was doing it 13.5 billion years ago. And the record shows it was doing it faster than anyone thought possible. The discovery of JADES-GS-Z 14-0 did not happen by accident. It was the product of the most ambitious systematic study of the earliest galaxies ever designed, executed by a large international collaboration over several years of careful planning, observation and analysis. Understanding how it was found is part of understanding what it means. The JADES program, the JWST, Advanced Deep Extragalactic Survey, was conceived before the James Webb Space Telescope launched. It was designed by a steering committee that included some of the most experienced deep field observers in the world, scientists who had spent careers learning every subtlety of how to extract the most scientific information from the deepest, most demanding observations that space-based astronomy can produce. The survey was allocated what are called guaranteed time observations, a category of telescope time reserved for the instrument teams and principal investigators who built the telescope's components as partial compensation for the years of work they contributed to its construction. The JADES team's guaranteed time was enormous by the standards of any previous deep field survey, Hundreds of hours of observing time on two of the telescope's most scientifically productive instruments, NIRCam and NIRSPEC. NIRCam, the near-infrared camera, is the telescope's primary imaging instrument. It produces deep images of the sky in multiple infrared wavelength bands, each chosen to isolate different physical features of distant galaxies. The combination of images at different wavelengths allows astronomers to construct the spectral energy distribution of a galaxy, the way its brightness varies across the spectrum, which encodes information about its distance, its temperature, the ages and masses of its stars, the amount of dust it contains, and dozens of other physical properties. At very high redshifts, one of the most useful features of a galaxy's spectral energy distribution is the Lyman break. Hydrogen in a galaxy absorbs photons at wavelengths shorter than 91.2 nanometers in the ultraviolet, which means that any galaxy will appear to have no flux, no light at all, at wavelengths shorter than that threshold. This complete cut-off of light below the Lyman limit, redshifted to whatever wavelength corresponds to that limit at the galaxy's distance, produces a characteristic dropout in the galaxy's colours. A galaxy at redshift 14 will appear completely invisible in filters designed to detect wavelengths below roughly 1.3 microns and will show up only in the longer wavelength filters. This dropout technique, combined with careful analysis of the colour ratios at longer wavelengths, allows astronomers to identify candidate high redshift galaxies from imaging data alone. These photometric candidates cannot be confirmed by imaging alone. They need spectroscopy, which means dispersing the galaxy's light into its component wavelengths and measuring where the cutoff and the emission lines fall precisely enough to determine an exact redshift. NIRSPEC, the near-infrared spectrograph, is what makes that confirmation possible. It uses a technology called the microshutter array, a grid of microscopic shutters each the size of a human hair that can be opened or closed individually under computer control. This allows NIRSPEC to place a spectroscopic aperture on hundreds of individual galaxies simultaneously, taking spectra of all of them at once rather than one at a time. In a single observation, NIRSPEC can confirm the distances and characterize the physical properties of hundreds of high redshift galaxy candidates selected from NIRCam imaging. The combination is extraordinarily powerful. NIRCam finds the candidates, NIRSPEC confirms and characterizes them, and the guaranteed time available to the JADES team meant that these two instruments could be applied to the same fields for hundreds of hours, reaching depths that required days or weeks of accumulated exposure time, finding objects too faint for any other approach. The specific field that contained JADES-GS-Z14-0 is called the Goods-South field, the Great Observatory's Origins Deep Survey South, one of two fields in the southern hemisphere that had been observed by Hubble and other telescopes for decades, and were among the most deeply studied patches of sky in the history of astronomy. The choice to target fields with extensive prior observations was deliberate. Every galaxy that Hubble had detected in those fields provided a calibration anchor for the Webb data. The longer wavelength images from Webb could be directly compared to the existing Hubble data to identify which objects were new detections, which were the same objects seen in more detail, and which were entirely new categories of object that Hubble had been unable to see at all. The JADES Origins field, the specific subset of Goods-South that received the deepest imaging in the fall of 2023, was the product of 5 full days of continuous STIRCam imaging on a single pointing. 5 days, accumulating signal from the faintest possible sources, building up enough photons from objects so distant that their contribution to any single brief exposure would be unmeasurable. The resulting images pushed further into the early universe than any previous imaging survey. Among the candidates identified in those images was a faint elongated source that appeared to have no flux below the wavelengths corresponding to a Lyman break at redshift 14. The source was close enough on the sky to a foreground galaxy at a much lower redshift that the team spent considerable effort verifying that the two were not physically associated, that the high redshift source was not simply part of the foreground galaxy, or a feature associated with its gravitational field. The verification was conclusive. JADES-GS-Z14-0 was distinct from the foreground galaxy. It was at a much greater distance, and its properties, its brightness, its colour, its spatial extent, were consistent with a galaxy at a redshift of around 14. The spectroscopic confirmation campaign that followed was the most ambitious single pointing in the JADIS program. A 75-hour investment of near-spec time on the JADIS Origins field, designed as the capstone observation of the entire survey, targeting the faintest and most distant candidates for spectroscopic characterization. Among those targets was JADIS GSZ 14-0. The near-spec microshutter array was configured so that one of the tiny apertures was positioned directly on the candidate galaxy. For 10 hours of observation, the light from that faint reddened smear was dispersed and accumulated on the instrument's detectors, and when the spectrum was processed, the Lyman break appeared exactly where it would appear if the galaxy were at a redshift of 14.32. The confirmation was, as the team described it, unambiguous. There was no alternative interpretation consistent with the data. The galaxy was at a redshift of 14.32. Its light had left it when the universe was 290 million years old. And the spectrum revealed, in addition to the redshift confirmation, the bright emission lines from ionized hydrogen and, through the supplementary MIRI analysis, the signatures of ionized oxygen. The team prepared 3 papers describing different aspects of the discovery. The first, led by Stefano Carniani, described the spectroscopic confirmation and the physical properties derived from the spectra. The second, led by Jake Helton, described the MIRI observations and the implications of the longer wavelength photometry. The third, led by Brant Robertson, described the implications for the broader population of early galaxies and what the discovery of JADES-GS-Z14-0 implied for the number of similarly luminous galaxies that likely existed at even earlier epochs. All 3 were released together on May 30th, 2024, accompanied by a NASA Science blog post that provided an accessible summary of the findings and was widely circulated in scientific and popular media. The response from the broader astronomical community was immediate. The discovery was recognized as the most significant deep field result since the telescope's first science operations, and as the clearest single object demonstration of the tension between the Webb observations and the predictions of the standard model that have been accumulating since those first deep fields were released in 2022. The significance was not merely the record-breaking distance. Records in this field are broken regularly enough that they have become almost routine. The significance was what the galaxy's properties said about the universe's operational efficiency in its earliest moments: the size, the stellar mass, the oxygen, the light of young stars filling every cubic light-year of a galaxy that should not yet have had time to exist. And then, less than a year later, the oxygen confirmation from ALMA arrived, adding a layer of precision to the chemical story and confirming, with the independent authority of a completely different observational technique, what the MIRI data had suggested. The picture was complete, or as complete as a single galaxy observed at one moment in its history can make a picture. There is more to learn. There will always be more to learn. But what has been learned from JADES-GS-Z14-0 is already enough to require a revision of our understanding of the early universe. And the people who will build that revision are working with the telescope right now. When a scientific observation is described as placing a model under severe tension, it means something specific. It does not mean the model is wrong in its entirety. It does not mean the fundamental physics that underlies it is incorrect. It means that the model, as currently formulated with the parameters currently assigned to it, does not fully account for what has been observed. The gap between prediction and observation is larger than can be explained by measurement uncertainty or random statistical variation. Something needs to change. The lambda CDM model, the standard model of cosmology, describes the universe in terms of 3 primary components: ordinary matter, the atoms and molecules and everything composed of them, comprising roughly 5% of the total energy content of the universe; dark matter, the invisible gravitational ingredient whose nature remains unknown, but whose gravitational effects are observed in the motions of galaxies; and the large-scale structure of the universe, comprising roughly 27%; and dark energy, the mysterious force that is driving the accelerating expansion of the universe, comprising roughly 68%. Within this framework, the formation of galaxies and large-scale structure proceeds according to a well-developed theoretical picture called hierarchical structure formation. Dark matter collapses first, because it interacts only gravitationally and does not couple to radiation the way ordinary matter does. It forms halos, gravitationally bound regions of concentrated dark matter, that grow over time by accreting surrounding material and merging with other halos. Ordinary matter falls into these dark matter halos, cools through radiative processes, collapses further, and eventually forms stars. The word hierarchical refers to the bottom-up nature of this assembly. Small halos form first because small density fluctuations collapse earlier in cosmic history, when the universe is denser and the gravitational collapse timescale is shorter. Large halos form later, as smaller halos merge and accumulate mass over hundreds of millions and billions of years. This means that the first galaxies should be small. They should be hosted in small, dark matter halos. They should contain relatively few stars. They should be dominated by the first chemically pristine generation of stars, without the heavy elements that come from multiple cycles of stellar birth and death. The observations from the James Webb Space Telescope and JADES-GS-Z 14-0 in particular suggest that the early universe was working more efficiently than this picture implies, not necessarily in a way that requires changing the fundamental physics of dark matter or gravity or the Big Bang itself, but in ways that require revising how we model the processes by which gas cools and collapses into stars within the dark matter halos that the standard physics produces. The most natural explanation, the one that requires the fewest departures from existing physics, is that star formation efficiency in the early universe was higher than it is today. The early universe was denser. The gas falling into dark matter halos was denser. The conditions for gravitational collapse were more favourable, and crucially, the feedback processes that limit star formation in the present-day universe, the energetic output of newly formed stars that heats and stirs and sometimes expels the surrounding gas, limiting how much of it can collapse into the next generation of stars, may have been less effective in the early universe for a variety of reasons. Some researchers have proposed that the first generation of stars may have formed in conditions that allowed a much larger fraction of the available gas to collapse without disruption. The very first star-forming clouds, forming from a gas that contained only hydrogen and helium and trace lithium, would have had cooling properties different from the metal-enriched gas that forms stars in the present-day universe. Different cooling properties mean different fragmentation patterns, different mass distributions for the resulting stars, different feedback strengths, and potentially different efficiencies of gas-to-star conversion. Other researchers have suggested that the dark matter halos in the early universe may have had different properties than the simulations predict, not necessarily because the nature of dark matter is different, but because the initial conditions of the universe, specifically the amplitude and shape of the primordial density fluctuations that seeded all subsequent structure formation, may have been slightly different from what the standard inflationary models assume. Inflation, the period of extremely rapid expansion that is theorized to have occurred in the first fractions of a second after the Big Bang, is responsible for producing the quantum fluctuations that grew, over the following hundreds of millions of years, into the density variations from which all galaxies ultimately formed. If the power spectrum of those fluctuations, the distribution of how large and how small and how common each scale of fluctuation was, had more power at small scales than the standard inflationary models predict, then small halos would have formed earlier and more abundantly in the early universe, giving galaxies a head start on their assembly. This is a possible modification to the standard picture. It is not a radical departure from it. It adjusts the initial conditions rather than the fundamental physics, and it is testable, in principle, by looking at the statistical properties of the galaxy population at very high redshifts and comparing them to the predictions of models with different assumed power spectra. The James Webb Space Telescope provides exactly the data needed to perform those comparisons, and teams around the world are doing so using the JADES data and the data from the SEERS, Cosmos Webb, and other Webb surveys to constrain the possible modifications to the standard model that are consistent with the observations. None of these teams has yet produced a consensus. The field is active, the data is rich, and the theoretical landscape is complex enough that different groups emphasizing different aspects of the observational evidence reach somewhat different conclusions about exactly how much revision the standard model requires and where precisely that revision should be applied. What is broadly agreed upon is this: the early universe, as revealed by the James Webb Space Telescope, was a more productive and more efficient place than the pre-Webb models anticipated. The degree to which this reflects new physics versus new parameter values within existing physics is still being determined. The role of JADES-GS-Z 14-0 in this conversation is to provide the most extreme, most precisely characterized single data point available, the object that most definitively sits outside what the models predicted and whose properties most directly require an explanation. It also provides something else. It provides a specific object to study in more detail as the James Webb Space Telescope continues its mission. The galaxy has been imaged in multiple wavelength bands. It has been spectroscopically confirmed by two independent instruments using two completely different observational techniques. It has been detected in the mid-infrared by MIRI. It has been detected by ALMA at millimeter wavelengths. Each of these detections adds information about its properties. Future observations could constrain the galaxy's kinematics, the motions of its gas and stars, which would allow estimates of its total mass including dark matter. They could characterize the distribution of stellar ages within the galaxy, providing information about when star formation began and whether it proceeded in bursts or continuously. They could measure additional chemical abundances beyond oxygen, providing a more complete picture of the galaxy's chemical enrichment history and the properties of the stellar populations that produced those elements. Each additional measurement tightens the constraints on the models. Each additional measurement makes the universe's story at 290 million years clearer and more specific. And each additional measurement, if the pattern of the last few years holds, will likely reveal something that the models had not fully anticipated. The universe, it turns out, is generous with its surprises. There is a boundary to everything the James Webb Space Telescope can see, and that boundary is not determined by the quality of its mirror, or the sensitivity of its detectors, or the number of hours astronomers are willing to invest in a single deep field observation. The boundary is determined by the age of the universe and the speed of light. The observable universe is a sphere centered on the Earth, or rather on wherever in the universe you happen to be, with a radius defined by how far light has been able to travel since the Big Bang. The universe is 13.8 billion years old. Light travels at roughly 300,000 kilometers per second. In 13.8 billion years, light can travel approximately 13.8 billion light years. But the observable universe is larger than that, for the same reason that the co-moving distance to JAD-ES-GS-Z14-0 is larger than its light travel distance. The universe was expanding while the light was travelling. The objects from which the oldest light arrived were closer to us when they emitted that light than they are now. Accounting for all of the expansion that has occurred since the first photons were released, the edge of the observable universe, the most distant points from which light could conceivably have reached us, is approximately 46 billion light-years away in every direction. The observable universe is in that sense a sphere roughly 93 billion light-years in diameter. It contains, by current estimates, at least 2 trillion galaxies. It contains all of the structure that the James Webb Space Telescope can ever observe, regardless of how long it operates, how deep its exposures become, or how sophisticated its instruments are. Beyond 46 billion light-years, nothing can reach us. The expansion of space between us and more distant objects is proceeding faster than the speed of light, which means that any signal from beyond that boundary, no matter when it was sent, will never arrive. The universe beyond the observable horizon is there. It is real. It follows the same physics as the universe inside the horizon. But it is permanently and irreversibly inaccessible. How large is the universe beyond the observable horizon? We do not know with precision because direct observation is by definition impossible. But analyses using the best available cosmological data have produced estimates. One study, applying Bayesian model averaging to the available measurements, concluded that the total universe is at least 250 times larger than the observable portion. If the universe is spatially flat, which the best current measurements marginally favour, the total extent may be infinite, 250 times larger in every direction. The sphere of what we can observe, 93 billion light-years in diameter, is like a single small room in a building so large that even its rough dimensions are uncertain. In that context, everything discussed so far in this narration, every galaxy in the JD's deep field, every candidate at high redshift, every universe breaker, every little red dot, JD's GSZ 14-0 itself, all of it is located inside that one small room. We have never observed anything outside it. We never will. This is not cause for despair. It is cause for a specific kind of intellectual humility. Every theoretical framework we have constructed to describe the universe, every simulation, every constraint on the parameters of the standard cosmological model, every prediction about what exists at high redshift and how galaxies form and evolve has been built from data inside that room. Whether what we observe in our room is representative of the total universe, whether the patterns we find in our observable volume hold throughout the rest of the unobservable cosmos, cannot be determined. The galaxy JADES-GS-Z14-0, surprising as it is within the observable universe, exists in a universe that is almost certainly far stranger and more varied than what we can see from our position within it. But let's step back from the maximum scale for a moment and return to something more immediate. The light from JADES-GS-Z14-0 crossed an extraordinary distance to reach us. But the instrument it arrived at was itself an extraordinary thing, a machine built with the precision of a system designed to hear a signal that had been travelling for longer than the Earth has existed. The James Webb Space Telescope weighs approximately 6,500 kilograms. Its mirror, 6.5 meters across, collects photons. Its sun shield, the size of a tennis court, blocks heat. Its instruments, cooled to within 40 degrees of absolute zero, detect signals at the extreme edge of what is physically possible to measure. And the signal it detected from JADES GS-Z14-0, the photons from a galaxy that existed 290 million years after the Big Bang, had been travelling for 13.5 billion years. The photons that landed in the James Webb Space Telescope's instruments in January 2024 departed their source, 9 billion years before the Earth existed. They were not going anywhere in particular. They were simply propagating outward from their source, in all directions, as photons do, carrying information about the galaxy that emitted them at a rate of 300,000 kilometers per second. For 13.5 billion years, across a universe that was expanding around them, they travelled. Almost all of them missed. Almost all of them travelled in directions that did not intersect with any detector. A vanishingly small fraction of them happened to be travelling in exactly the right direction at exactly the right time, to fall into the hexagonal gold-coated mirror of a space telescope launched by human beings from a space centre in French Guiana on the 25th of December 2021. That is not poetry. That is physics. And it is as close to poetry as physics gets. The universe does not care whether its signals are received. The photons from JADES-GS-Z14-0 did not set out to be observed. They do not know they carry information about the most distant confirmed galaxy in the universe. They do not know they carry information about oxygen in a galaxy that assembled itself in the first 290 million years of cosmic time. They are simply photons, propagating at the speed of light, doing what photons do. We are the ones who care. We are the ones who built the mirror and cooled the detectors and unfolded the sunshield and pointed the telescope at a grain of sand in the sky, and waited 10 hours for enough of those ancient photons to accumulate and tell us something. That is what the discovery of JADES-GS-Z14-0 actually is at its most fundamental level. A choice to build something extraordinary, point it at something dark, and listen for something that was not expected, and hear something even more unexpected than hoped. To fully appreciate what JADES-GS-Z14-0 reveals about the early universe, it helps to understand, in as much detail as the current evidence allows, what preceded it. What was the universe doing in the hundreds of millions of years before the galaxy we have been discussing had assembled itself? The cosmic microwave background, the afterglow of recombination, gives us a precise snapshot of the universe at 380,000 years. At that moment, the universe was a nearly uniform sea of hydrogen and helium, with temperature variations of about 1 part in 100,000, the tiny residual imprint of the quantum fluctuations from the inflationary period. Those tiny variations, those 1 in 100,000 density differences scattered across the sky, are the seeds of everything that followed. Every galaxy, every cluster of galaxies, every supercluster and filament and void in the cosmic web, all of it grew from those tiny overdensities and underdensities in the 380,000-year-old universe. After recombination, as the photons streamed away in all directions and the matter was left behind to cool and move freely for the first time, the slightly overdense regions began to pull in material from their surroundings. This is gravity doing what gravity does, patiently, relentlessly, across timescales that make human civilization look like a blink. The first structures to form were not galaxies. They were dark matter halos, gravitationally bound clumps of the invisible material that dominates the mass content of the universe. Dark matter interacts only through gravity. It does not couple to radiation, it does not emit or absorb light. After recombination, when ordinary matter was finally free to respond to gravity, without being dragged around by the photon field, the dark matter halos that had already been quietly assembling since the early universe provided gravitational wells for ordinary matter to fall into. Hydrogen and helium gas fell into these halos. As it fell, it compressed. As it compressed, it heated. As it heated, it radiated energy, losing heat and compressing further. This cooling and collapsing process, called the Jeans instability in the language of fluid dynamics, applied to astrophysics, eventually produced regions dense and hot enough that the pressures and temperatures at their centres exceeded the threshold for nuclear fusion. The first star was born. We have never observed a population 3 star, as the first generation is called, directly. They formed and died in an era before the James Webb Space Telescope could observe them, in galaxies too small and too faint to be individually detected, even by the most sensitive instruments yet built. But their theoretical properties have been studied extensively, and the signatures of their existence, the chemical enrichment they produced and distributed, can be inferred from the compositions of the oldest surviving stars in the universe, and from the chemical properties of the earliest galaxies that have been observed. Population 3 stars, the models suggest, were different from the stars that form today in one critical way. They formed from gas that contained essentially no metals. Gas with no carbon, no oxygen, no silicon, no iron, just hydrogen and helium and trace lithium. And because the processes by which gas clouds cool and fragment into individual stars depend strongly on the presence of heavy elements, gas with no metals cools differently. It cannot radiate energy as efficiently at lower temperatures. This means it must be compressed to higher temperatures and pressures before it becomes unstable to gravitational collapse and fragments into stars. Higher collapse temperatures and pressures mean larger, more massive stars. The first stellar population, the theory predicts, was dominated by stars of extraordinary mass, some of them perhaps hundreds of times the mass of our Sun. These stars burned hot, lived fast and died young, their entire lifespans measured in a few million years. When they died violently. Stars above roughly 140 times the mass of our Sun are theorized to undergo a particular type of explosion called a pair instability supernova, triggered by the production of electron-positron pairs in the stellar core at extremely high temperatures. These are among the most energetic stellar explosions theorized to occur in the universe, capable of completely disrupting the star without leaving any remnant, scattering the entire mass of the star, including all the oxygen and carbon and heavier elements synthesized in its interior, into the surrounding space. Other massive population 3 stars would have collapsed directly to black holes, swallowing their interiors without an explosion, producing the seeds that would eventually grow into the supermassive black holes at the centers of galaxies. This direct collapse pathway is one of several mechanisms proposed to explain how the first generation of supermassive black holes formed, and it is particularly relevant in the context of JD's GS Z14-0 and the broader question of how early the universe's massive black holes assembled. The supernovae from the first generation of stars, pair instability or otherwise, distributed their chemical products into the surrounding intergalactic medium. This is stellar nucleosynthesis in action, the process by which the universe enriches itself with elements heavier than hydrogen and helium. The enriched gas, now containing oxygen and carbon and nitrogen and the other products of the first stellar lifetimes, cooled more efficiently than the pristine gas from which the first stars had formed. That more efficient cooling allowed it to fragment more readily, to collapse into smaller and more numerous stars, to produce a second generation with a broader range of masses more similar to the stellar populations we observe today. The second generation formed in a universe that was, for the first time, not chemically pristine. Its stars contained the oxygen produced by their predecessors. They carried in their composition the record of the first stellar deaths, and in JADES-GS-Z14-0, at 290 million years after the Big Bang, we see the accumulated result of that first cycle. The oxygen detected in the galaxy's spectrum is the oxygen that the first generation produced and distributed. The stars that fill the galaxy are at least partly, and perhaps mostly, descendants of that first cycle of birth and death. The timeline is extraordinary. Population 3 stars forming within the first 100 to 200 million years, those stars living for a few million years, those stars dying and enriching the gas, that enriched gas cooling and collapsing into second-generation stars. Those second-generation stars and the continued infall of gas from the surrounding intergalactic medium assembling in the gravitational well provided by a dark matter halo that had been growing since recombination into a galaxy with several hundred million solar masses and a diameter of 1,600 light-years. All before the universe was 300 million years old. The universe was working fast. The universe was working with an efficiency that the standard models, calibrated on billions of years of subsequent observation, had not fully accounted for, and JADES-GS-Z14-0 is the clearest evidence we have of that efficiency in operation. What drove it? Why was the early universe able to produce this result in such a compressed time frame? The answer is not fully known, but the leading hypothesis, the one most consistent with the available data and requiring the least departure from known physics, is simply that the early universe provided conditions for star formation that were more favourable than the conditions that exist today. Higher densities, more gas per unit volume, dark matter halos that, while small by the standards of later cosmic history, were surrounded by abundant pristine gas ripe for accretion and collapse. Cooling timescales that, despite the absence of metal line cooling in the first generation, were short enough relative to the available time that the first stars could form before the universe had expanded and cooled too much. And perhaps, most importantly, a universe in which the feedback that limits star formation in the present epoch had not yet had time to operate at scale. Billions of years of stellar feedback, the accumulated heating and stirring from billions of supernovae and billions of stellar winds and the energetic output of billions of active galactic nuclei have raised the entropy of the intergalactic medium to a level that makes it harder to collapse into new stars. The early universe had not yet accumulated that feedback. It was fresh, it was dense, and it was building with a speed that we are only now beginning to measure. There is a particular quality to the work of observational cosmology that is unlike most other scientific endeavours. It requires a specific kind of patience, not the patience of waiting for an experiment to run, or for data to accumulate, or for a paper to be reviewed and accepted, though it requires all of those things too. It requires the patience of existing in deep time, of holding in your mind simultaneously the present moment and moments 13 billion years in the past, of understanding that every image on a computer screen in a room in Baltimore or Tucson or Pisa is a message from an epoch that preceded the formation of our solar system by billions of years. The people who built the James Webb Space Telescope worked on it for 30 years. Some of them spent their entire careers, from graduate school to retirement, contributing to a project that would be completed after many of them had moved on to other things. The instrument that found JADES-GS-Z14-0 was in development for longer than the scientists who found it had been alive in some cases. That kind of investment, a 30-year sustained effort by hundreds of scientists and engineers across multiple continents and space agencies, is itself a remarkable expression of something. Not simply ambition, though it required extraordinary ambition. Not simply resources, though it required $10 billion and the sustained institutional commitment of NASA, the European Space Agency, and the Canadian Space Agency. But a specific belief that the universe had things to tell us that we had not yet heard, things that were worth waiting 30 years to learn. The universe did not disappoint. It told us about a galaxy from 290 million years after the Big Bang that was brighter and more massive and more chemically mature than it should have been. It told us about oxygen in a place where oxygen was not supposed to have arrived yet. It told us that the early universe was working at an efficiency that our most carefully constructed models had not anticipated. And it told us all of this in a spectrum, a graph, a pattern of wavelengths and intensities that, to a trained eye, reads as clearly as text. The Lyman break at a specific wavelength, indicating the galaxy's distance. The emission lines from ionized hydrogen and oxygen, indicating the presence of energetically active gas. The overall shape of the spectral energy distribution, indicating the dominance of stellar light over black hole light. The people who processed that spectrum in January of 2024 were sitting in front of computer screens in ordinary rooms with ordinary coffee mugs and ordinary concerns about ordinary things. And then the numbers came back, and the numbers said 14.32, and the ordinary concerns fell away for a moment in the presence of something that had travelled 13.5 billion years to be read on a Tuesday morning. That is what observation is at its best. The universe is not opaque. It is broadcasting continuously in every direction, from every galaxy at every distance. The information is all there in the light. The only requirement is an instrument sensitive enough to collect and decode it, and a community of scientists patient and skilled enough to build that instrument and point it at the right patch of darkness. The darkness is never empty. It is filled with messages from the beginning. Consider for a moment the specific chain of causality that produced the discovery of JADES-GS-Z14-0. In the early universe, a galaxy assembled itself from dark matter and gas. That galaxy's stars produced oxygen and scattered it through the galaxy's interstellar medium. The galaxy emitted light at visible ultraviolet wavelengths as its young stars burned. That light travelled outward from the galaxy in all directions. The universe expanded around it, stretching the light from ultraviolet to near-infrared to mid-infrared over 13.5 billion years of travel. The light passed through empty intergalactic space, through regions of neutral hydrogen in the epoch of reionization that absorbed some of its shorter wavelength photons, through the grown-up universe of the present day that contains the thin, hot plasma of the cosmic Webb's filaments, and the cool, neutral gas of galaxies like our own. Meanwhile, on a small rocky planet in the outer spiral arm of an unremarkable galaxy, in the local group, organisms that had evolved from single-celled ancestors over 3.8 billion years developed language, and then writing, and then mathematics, and then telescopes, and then spectrographs, and then space telescopes, and then a $10 billion space telescope specifically designed to be sensitive to the wavelengths in which the ancient light of the earliest galaxies arrives. They launched it on Christmas morning, 2021. It unfolded correctly, all 344 steps. It cooled to operating temperature. It pointed at a patch of sky in the constellation Fornax. It waited 10 hours. And the light from JADES-GS-Z14-0, which had been travelling since the universe was 290 million years old, fell into the hexagonal gold-coated mirror and was focused and dispersed and red. The universe and the observer, separated by 13.5 billion years and 33.8 billion light years, connected by a thread of ancient photons and a mirror cold enough to hear them. That is what happened on a Tuesday in January 2024. That is what the discovery of JADES-GS-Z14-0 actually was. The rest of it, the science and the implications and the revisions to the models and the questions it raises about the early universe's efficiency, all of that is real and important and worth understanding in detail. But underneath all of it is that simpler thing, a signal sent from the beginning of the universe's history, received at the beginning of the universe's last era, in which signals from that history can still arrive. We are, in cosmic terms, lucky to be here at the right time. The window for reading the universe's earliest messages is open, but it will not remain open forever. There is something about the timing of the James Webb Space Telescope's operation that is not widely understood outside the community of cosmologists who have thought carefully about it. We happen to exist at a specific moment in the history of the universe when the full record of that universe's past is accessible. All of it. Every galaxy at every distance. The cosmic microwave background. The first galaxies at the edge of observable time. The complete history of cosmic structure formation, written in the light of trillions of stars scattered across 46 billion light-years of observable space. This will not always be the case. The universe is expanding, and the expansion is accelerating, driven by the dark energy that comprises 68% of the universe's total energy content. As the universe expands, the more distant galaxies recede faster. For galaxies that are already sufficiently distant, the space between them and us is expanding faster than the speed of light. Those galaxies have already crossed what cosmologists call the cosmic event horizon. Any signal they emit today will never reach us. They are irreversibly gone from our observable universe, even though they still exist somewhere in the broader cosmos. JADES-GS-Z14-0, the galaxy that has been the subject of this entire narration, is already in this category. Its current location, accounting for 13.5 billion years of expansion since the light we received was emitted, is far beyond the cosmic event horizon. Any signal that galaxy emits today is travelling away from us into an expanding space that will never bring it to our instruments. The light we have from JADES-GS-Z14-0 is the only light we will ever receive from it. No future observation, no matter how powerful, will add to our picture of that specific galaxy at any time other than 290 million years after the Big Bang. Over the next 100 billion years or so, roughly 7 times the current age of the universe, every galaxy beyond our local group will cross the cosmic event horizon and disappear from our observable universe. The local group, the small collection of galaxies of which the Milky Way is a member, is gravitationally bound. Its members are being pulled together by their mutual gravity, which is stronger in their vicinity than the dark energy-driven expansion. They will remain together, and a civilization in the far future will still see the galaxies of the local group. But everything beyond, every galaxy in the Virgo cluster, every galaxy in the Laniakea supercluster, every galaxy in the hundreds of thousands of observable clusters and superclusters and filaments that populate the current observable universe, all of that will have receded beyond the event horizon. At that point, a civilization looking at the sky with the most powerful telescope they could build would see no external galaxies. They would see only the stars of the merged remnant of the Milky Way and Andromeda, and their smaller companions, everything else dark. The cosmic microwave background would have been stretched by hundreds of billions of years of additional expansion to wavelengths, so long as to be undetectable by any physical instrument. There would be no evidence, in the observable sky, that the universe had ever been smaller or hotter. A civilization arising in that era, and applying every observational and theoretical tool available to them, would very likely conclude that the universe consisted of a single, stellar system adrift in infinite static space. They would not see the expansion. They would not detect the cosmic microwave background. They would not see distant galaxies with redshifts. There would be no evidence from which to reconstruct the Big Bang, the early universe, or any of the history that we can read from our current position with so much clarity. Everything we know about cosmic history, everything the James Webb Space Telescope is telling us about galaxies at redshift 14, and the conditions of the early universe will be inaccessible to them. Not because they are less intelligent or less capable, or have built worse instruments, but because the universe will have expanded enough that the evidence will no longer be within reach. We live in the only epoch when the evidence is still there. That is not a metaphor or an exaggeration. It is a physical fact about the timing of our existence relative to the expansion history of the universe. We are here, with the James Webb Space Telescope operational, at what is, in cosmological terms, exactly the right moment. The window during which the universe's full history is legible is open. It will not close in human lifetimes, or in the lifetime of our species as currently constituted. But on the scale of cosmic time, it is closing. In that context, the investment in a telescope like the James Webb Space Telescope is not merely a scientific project. It is a civilization's recognition that the window is open right now, and that building the best possible instrument to read through it at this specific moment in cosmic history is one of the most important things that a spacefaring species could choose to do with its resources and its ingenuity. The future of the observations is already being planned. The Roman Space Telescope, a NASA mission designed with a wide-field infrared camera and a coronagraph for exoplanet imaging, will complement the Webb's deep-field capabilities with surveys covering much larger areas of sky at comparable depths. Proposed missions, including the Habitable Worlds Observatory and the Lynx X-ray Observatory, would extend humanity's observational reach into the ultraviolet and X-ray regimes, providing complementary views of the early universe and the high-energy processes that shaped it. On the ground, the extremely large telescope currently under construction in Chile and its siblings, the 30-metre telescope and the Giant Magellan Telescope, will provide spectroscopic capabilities at visible and infrared wavelengths that complement Webb's space-based observations. With a 39-metre primary mirror, The ELT will be able to take spectra of some of the galaxies Webb has imaged, characterizing their chemistry and kinematics in more detail than the Space Telescope alone can achieve. And ALMA, the Atacama Large Millimeter Array that provided the independent confirmation of oxygen in JADES-GS-Z14-0, continues to observe and will continue to provide the millimeter wavelength view of the earliest galaxies that complements the infrared observations from space. The story of JADES-GS-Z14-0 is not finished. It will be studied more, characterized more completely, used as a reference point against which future discoveries at even earlier epochs will be compared, and what those future discoveries reveal about the universe's efficiency in its first 200 million years. The era that lies beyond even the remarkable object at the centre of this narration will either confirm or extend what JADES-GS-Z14-0 has already told us. The early universe was fast, it was efficient, it was building things that the model said it should not yet have had time to build. And the more clearly we see it, the more precisely we measure it, the more specifically we characterize the oxygen and the stars and the structure of its earliest galaxies, the more clearly that message comes through. The universe was in a hurry at the beginning. We are just now learning how much of a hurry. You are right now on a planet. That planet is the third of 8 planets orbiting a star of middling size and middling age, 4.5 billion years into its 10 billion year lifespan, in the outer regions of a spiral galaxy called the Milky Way. The Milky Way is a galaxy of ordinary proportions, roughly 100,000 light-years in diameter, containing somewhere between 100 billion and 400 billion stars, of which our Sun is one. It is a member of a small collection of galaxies called the Local Group, which itself is a peripheral member of a larger gravitational structure called the Virgo supercluster, which is itself part of a supercluster of superclusters called Laniakea, a structure 500 million light-years across containing roughly 100,000 galaxies. All of that, from the planet beneath you to the supercluster that contains your galaxy, exists in a universe that is 13.8 billion years old, and that, from its earliest moments, was building itself with a speed and an efficiency that we are only now beginning to measure. In the direction of the constellation Fornax, in a patch of sky you cannot find with the naked eye, because it appears blank and empty, a galaxy existed 290 million years after the Big Bang. It was called JADES-GS-Z14-0. It was over 1,600 light-years across, roughly the width of the spiral arm in which our own solar system drifts through the Milky Way. It was filled with young, hot stars burning at full intensity, producing the same kinds of photons that stars in our galaxy produce right now. In the same way, for the same physical reasons, it contained oxygen. Oxygen that had been forged inside stars and scattered by supernovae and incorporated into gas clouds and finally fused into a new generation of stars and their surrounding medium. All before the universe was 300 million years old. It was discovered by 10 hours of observation from the James Webb Space Telescope, a machine that spent 30 years in development, cost $10 billion to build and launch, successfully completed 344 sequential steps of mechanical deployment in the vacuum of space, and has been reading the universe's earliest light from a gravitational balance point 1 million miles from Earth since mid-2022. The light from JADES-GS Z14-0 had been travelling toward that telescope for 13.5 billion years. It left its source 9 billion years before the Earth existed. It travelled through the epoch of reionization, when the neutral hydrogen fog of the early universe was gradually burned away by the first galaxies. It passed through the long Middle Ages of cosmic history, when galaxy clusters were assembling and the cosmic web was growing, and the rate of star formation across the universe was rising toward its peak around 10 billion years ago, before beginning its long decline toward the relative quiet of the present epoch. It kept travelling as the solar system formed, as life evolved on Earth, as human beings developed language and writing and mathematics and astronomy. It was still travelling on December 25th, 2021, when the Ariane 5 rocket lifted off from French Guiana with the telescope inside, and then it arrived. On a Tuesday in January 2024, some of those photons fell into the mirrors of the near-infrared spectrograph aboard the James Webb Space Telescope and were sorted by wavelength onto a detector array, cooled to within 40 degrees of absolute zero, and a spectrum was produced. And when the spectrum was processed and the numbers read out, the redshift was 14.32, and Stefano Carniani and Kevin Hainline and Brant Robertson and Jake Helton and their colleagues and collaborators looked at those numbers and said the word that kept coming back in every announcement and every paper and every interview in the months that followed: unanticipated. The universe, it turned out, had not consulted the models before building its first galaxies. It had built them faster and more efficiently than the models allowed for. It had filled them with oxygen at an age when the models said it was barely time for the first stars to be born. It had assembled 600 light-years of stellar fire and interstellar gas and dark matter scaffolding, and called it a galaxy at a moment when the universe was 2% of its current age. And it had kept the light from that moment travelling through 13.5 billion years of expanding space to be caught by a gold-coated mirror on a particular Tuesday afternoon. There is nothing required of you in response to this. The universe does not need your acknowledgement. The discovery of JADES-GS-Z14-0 does not demand anything from you. It simply happened, and it is now part of what is known, part of the body of knowledge that humanity has accumulated about the place it inhabits. But there is something available in the knowing of it, if you choose to sit with it for a moment. A particular quality of perspective that comes from holding simultaneously the scale of the universe and the scale of a Tuesday afternoon in a control room in Baltimore. The largest thing and the most ordinary thing, the universe in its infancy and the scientist at a keyboard. The light that travelled 13.5 billion years and the detector cold enough to feel it. Both of those things are real. Both of them were necessary for the discovery to occur. The universe had to produce a galaxy at 290 million years that was bright enough to be detected. And human beings had to build a telescope sensitive enough to detect it. The universe and the observer. The ancient signal and the instrument built to receive it. The thing that happened before anything else existed, and the species that came along 13.5 billion years later and decided to look. That is what this is. That is what the story of JADES-GS-Z14-0 is, at its most fundamental. Not just a discovery, not just a record broken or a model revised or a paper published. A moment of contact between a civilization 13.5 billion years into the universe's history and a galaxy that existed near its beginning. A thread of ancient light, stretched by expansion and absorbed by a mirror and decoded by spectrographs and processed by computers and finally read by human eyes on a Tuesday morning. The window is open, the telescope is still pointing, the surveys are still running, the data is still coming in. There may be something older than JADES-GS-Z14-0 waiting to be found in the first 200 million years. There may be a galaxy from an epoch when the first generation of stars had barely formed, carrying in its spectrum the signature of processes that the standard model did not predict, and that will require decades of new theoretical work to explain. There may be oxygen in a galaxy older than this one. There may be things we have not yet thought to look for. The universe is not opaque. It is broadcasting in every direction, from every epoch, in every wavelength. It has been broadcasting for 13.8 billion years, and we are here in the brief cosmological window when all of that broadcast is still receivable, with the best instrument ever built for receiving it. Let that sit with you for a while. The dark is not empty. It never was. There is one more thing worth saying before this narration closes, and it concerns the nature of scientific discovery itself, as demonstrated by the story you have been listening to tonight. Science is sometimes described, in popular accounts, as a process of accumulating facts. A thing is discovered, it is added to the list of known things. The list grows, knowledge increases. This description is not wrong exactly, but it misses the most important part. The most important part is not the accumulation, it is the surprise. The moments when the list does not accommodate a new item without revision, when the new discovery requires that previously established items be reinterpreted or qualified, or recognised as incomplete descriptions of a more complex reality. JADES-GS-Z14-0 is one of those moments, not because it invalidates the standard model of cosmology, which it does not because it proves that the Big Bang did not happen, which it does not, but because it demonstrates, with the clarity and precision that direct spectroscopic measurement provides, that the early universe was operating at an efficiency that the model, as calibrated from billions of years of subsequent observation, had not predicted. The model needs to grow to include it. That is not a failure of the model. That is science working correctly. Models are not final answers. They are the best available descriptions of reality given the observations in hand. When new observations arrive that the model does not fully account for, the model is revised, extended, deepened, and the model that emerges from that revision is more accurate than the one that preceded it, because it has been tested against a harder set of observations and survived. The James Webb Space Telescope is providing harder observations than anything that came before it. The models are being tested against data from the cosmic dawn, from the first 300 million years of the universe's history, for the first time, and the models are being revised in response, in ways that will ultimately produce a more accurate and more complete picture of how the universe assembled itself from the first quantum fluctuations of inflation to the complex structured cosmos of the present day. That work is ongoing. It will continue for decades. The James Webb Space Telescope was designed for a minimum 10-year mission, with fuel reserves that may allow it to operate for 20 years or more. In that time, it will accumulate observations of the early universe that dwarf what has been collected in its first 3 years. It will find more galaxies like JADES-GS-Z 14-0. It may find galaxies older. It may find, in those older galaxies, chemical signatures that push the timeline of stellar evolution even earlier than the oxygen in JADES-GS-Z 14-0 already has. It may find something that nobody currently expects. That is, after all, what it has been doing since it first opened its eye. The universe is vast beyond intuition and old beyond comprehension and structured in ways that we are still discovering. JADES-GS-Z 14-0 is one point of light in a field of thousands of points of light in an image covering a patch of sky the size of a grain of sand, in an observable universe containing at least 2 trillion galaxies, in a total universe that is almost certainly far larger than the portion we can see. And yet that one point of light, that faint, elongated smear in the direction of Fornax, has told us something that the entire history of astronomy, before January 2024, could not have told us. It has confirmed that the universe was building galaxies with real stars and real oxygen and real chemical histories, in its first 290 million years. It has demonstrated that the efficiency with which the early universe assembled its first structures exceeded the predictions of the best models built from all prior observations. It has made the universe stranger, more surprising and more interesting than it was before we knew it existed. That is what discovery does. That is what the James Webb Space Telescope is doing, one deep field exposure at a time, one 10-hour spectrum at a time, one galaxy from the edge of the observable universe at a time. You're listening to this narration in whatever moment you're in, and the light from JADES